Well, hello. The team
Hello.
members are Ryan, Tyler, Garrett, and Anka. All of us are graduating seniors in the electrical engineering program at ASU. Our mentor, Raja Ayanar, is a ASU professor and mentor. He assisted us with his wealth of knowledge in the area of resilience and reliability when there's extreme penetration, uh, solar penetration in the distribution system. Our solution is to provide the most cost-effective means of reducing grid dependence while adding as much value to the system as possible. With little rooftop availability in the areas, low-cost ground mount systems have been designed. Difficult to match utility rate meant the cost of a large system was not really economical. We decided to design a system that remained below the minimum campus load to avoid net metering and impacting the distribution system, feeling this is the most economical solution. Agrivoltaics, a key aspect of the value that comes with this design. Battery storage is optional for resiliency of this science center. And it's the university's decision if the additional cost of the battery brings enough value to resilience of the science center at this time.
The main deliverables were split among us with collaboration throughout the process. We held weekly meetings, including the mentor, and maintained frequent communication with instant messaging. Utilizing agendas, meeting notes, a Gantt chart, and a shared drive for file sharing have all been essential for collaboration. 2 ground mount systems are proposed in 2 separate areas of campus to produce a total of 907 kilowatts, one in the geothermal field and one in the athletic field. Modules be produced by Sonali Solar, a partner with Cheyney University. The total system will have an annual production of 1,221 megawatt hours, an average yield of 1.3 megawatt hour per kilowatt. The systems will be raised 8 feet to provide space for agrivoltaics. The Sonali module specification sheet did not list every characteristic, including efficiency. This efficiency was assumed based on similar models at 20%. These models produced 360 watts. Aurora irradiance data showed 100% tilt orientation factor with 95% solar access and annual total resource factor. This was accomplished by avoiding placement near obstructions and setting a spacing between arrays at 8.5 feet to avoid self-shading. A 500 kilowatt hour containerized battery system by Green Sun Solar has been selected. The lithium iron phosphate chemistry will provide a longer battery life and depth of discharge of 80%. Jinlong Solus inverters are used with sizes of 40, 60, and 80 kilowatts. Ingeteam combiner boxes are used. Opting to use several inverters rather than one allows the system to operate continuously throughout maintenance, as well as better power output during partial shading.
Expected operation, the science center or athletic field system, and battery will feed into an AC panel, then into the building and out to the distribution system. During an outage, the science center will disconnect from the distribution system and will be fed using the battery and PV system for a minimum of 1 hour. The geothermal system will feed directly into the distribution system through a step-up transformer and separate from the system during an outage. Shown here is the power output for the first week of January and July. This gives good representation of the power output during seasonal daylight extremes. If the university chooses a cash purchase, students could study power output using agrivoltaics, adjusting panel angles, or other creative ideas to maximize power output or yields. Having the smaller inverters allows the study of the smaller portions of the PV system, as well as the ability to study them alongside a control group. The container battery was chosen for a turnkey solution. The container comes with all the systems needed to operate the battery safely. The lithium iron phosphate chemistry is capable of deep cycling, is environmentally friendly, and is very stable, making it ideal for storage solutions. The battery is designed to support the science center for a 1 hour outage during peak usage, starting at 60% capacity. If the critical load in the science center could be isolated or reduced, longer outage periods or maybe islanding are possible, but more information is needed to make this decision. The battery is cycled from 100% to 60% for battery health, and the battery is A battery size for peak shaving has negative economic value at this time. Overvoltage is the main concern on the distribution system when connecting PV systems. This happens when the PV system exports power onto the distribution system. Our proposed system falls below the minimum power usage for the university, so overvoltage is not a concern. This is supported using the Open DSS heat map that was given to us. The connection points are capable of handling much more than the proposed systems. This gives the university the option to build out more solar in the future as prices fall or their cost of energy goes up.
We want to analyze the construction cost per watt of our total system. Having a fully ground mount system, we can determine the cost per watt given the individual sizes of each. For our athletic field size of 349 kilowatts, there was a system cost of $1.85 per watt. Our corresponding cost for our geothermal field system of size 558 kilowatts is $1.61 per watt. With the utility benchmark as reference, our total system cost per watt comes out to $1.73 per watt. Given market standard, we as a team wanted a project IRR of 10%. This will lead to a reasonable cost for investors and ultimately gain more interest in a project of this kind. Given project sizing and cost, a PPA price was determined to be $0.1071 per kilowatt hour. This was chosen to produce a net present value of $0 to accommodate investor requests. With system costs and PPA prices developed, we determined an investor sale price of $1,823,193. With the electricity prices the campus pays as low as it is, this is a hard selling point as we move forward on the project. Our goal here is to find as many incentives as possible for the customer to bring down the overall price of our project. A customer analysis was conducted to help the campus know ultimately what they're getting out of our system. We can break our model up into the cost of our PV system plus the cost of our energy storage system. Our 2 PV array cost came out to $1,560,000 with a federal ITC tax incentive of $405,000. Our energy storage system came out to $225,000 with a federal ITC tax incentive of $58,500. This altogether totals $1,785,384. This was the initial price the university would pay given a cash purchase option. It is important to model our system with the operating and maintenance costs taken into consideration. For the operating maintenance costs of 1 cent per watt escalating annually at a rate of 2% and a battery replacement in the 15th year, a total system cost with O&M over 30 years comes out to $2,235,513. As shown in the bottom figure, with a set PPA price, our selling price is just too high to make this system economically viable. As the initial cash purchase option, however, does show that eventually, with a 30-year system lifetime, the initial cash investment will be made back. This is modeled by showing the electric bill saving over a 30-year system lifetime. This electric bill saving comes out to $2,358,004. This means that a net cash flow of $122,491 is going to be coming to the campus. With the energy prices the campus paying was so cheap, it was a challenge as a team to make a system to campus requirements that proved economically feasible. The direction the team decided to focus on was a resilience model to better prepare the campus for outages. As we model our system that includes an energy storage system, the campus will have to decide if the system of this size is worth including for the future of the school.
We're trying to achieve buy-in from the community by helping Cheyney University develop a climate action plan. One of the goals will be to reduce campus consumption of natural gas and electricity by expanding PV and battery storage. Establishing good communication between us and the university builds trust and community buy-in, creating a long-term relationship with the university. We looked into the university's master plan and principles and considered them when we did our design. Soil survey was completed using the Natural Resource Conservation System Service online tool, but showed no issues. No historical locations were found too close to the sites using the National Register of Historic Places. FEMA flag mapping showed some areas close to the geothermal field, but it is not expected to be a concern. National Wetlands Survey was also reviewed and showed no overlapping areas of proposed sites. We could not find any abandoned pipelines, wells, irrigation ditches that could affect our PV panels placement. Cheyney resides across 2 counties and also 2 different Thornbury townships. Permitting would be required for both counties and townships. Specific policy was not found for the township in Delaware County. The Chester County Thornbury Township ordinances were assumed satisfactory for both areas. We have accounted for ordinance by keeping all transmission lines underground. We'll need approval from the township to install the solar panels if a historic structure exists within 100 feet of our installations. The height of ground mount installations need to be less than 12.5 feet, which the system will meet despite being raised. The sites are also located within vehicle access and 20 feet of clearance from property lines as required. Any renewable energy system connected to the utility grid will require written authorization from the local utility company, which is PECO, acknowledging and approving such connection. In order to make sure we do follow guidelines for interconnection of generators to PECO's distribution system, we need to consult PECO's Gray Book. It is for large generators with applications rated at greater than 50 kilowatt. The Gray Book provides guidance to ensure that generators operated by customers connected to PECO's distribution lines will not impact the quality of service to other customers or jeopardize PECO's equipment. Assuming the system design with battery for resilience is completed at the end of the competition, an approximate timeline can be generalized. The design will be completed by the end of April, at which time we can start the permitting process. We estimate permitting to take approximately 2 months. Procurement will follow, and considering the supply issues we're facing right now, we estimate that to last approximately 9 months. Construction, as mentioned in the rules of the competition, will last 8 months. We're looking at an estimated in-service date of November 2023. Some of the risks we might encounter are related to the supply chain issues we're currently facing right now. For this reason, we're allocating 9 months in lead time for procurement.
With this plan, Cheyney University will have first steps toward green energy. Providing an area for agrivoltaics will offer many opportunities for this university to use the space for educational opportunities and to harness their partnerships in a new way. Agrivoltaic space can be used for animal grazing, apiary, and wildflowers, or growing crops. Students may use the space for research that can tie in with Cheyney partners such as Urban Farms and Advanced Alchemy Labs, who both work in agribusiness and farming.
That is all.